So, quote here by Isaac Asimov. Beginning students of chemistry often think of the science as a mere collection of disconnected data to be memorized by brute force. Not at all. Just look at it properly and everything hangs together and makes sense. This is actually why I like chemistry more than biology or other things. It's not just memorizing. There's just too much memorizing in biology for me. Too much. When I took biochem, I liked that a lot because then we looked at like the mechanisms of biology, and then that made sense to me. But pretty much everything in chemistry, if you can figure out what that underlying principle is, then that gives you all the information about the other things. And in general, I try to give you that underlying principle, try to highlight that. So for like gas laws, it's kinetic molecular theory, right? That kind of just explains why ideal gases behave the way they do. Here, it's mostly going to be effective nuclear charge. And we'll talk about that when we get to it. It's not hard to calculate, and it predicts a lot of things. All right, so Dmitry Mendeleev was this dude who looked at all the elements that they had at the time, which their periodic table had way fewer elements. But he thought there must be a pattern to all of these elements. Just pull this down. And so he basically took them and started sorting them in any way that he could. The first way, I think, was to sort them by atomic mass. So if you sorted them by atomic mass, basically you get just a straight line of elements or a list of elements. And then he said some of these actually have repeating properties, so things like lithium and sodium, beryllium, magnesium. So maybe those should go in vertical columns together. And he sorted the whole thing out so that with what he had at the time, the periodic table made sense, and there are multiple trends all over the periodic table. Yeah. There are some weird places where the atomic masses don't line up. Tellurium and iodine. The tellurium's 127, iodine's 126. The atomic mass actually goes down there. But otherwise, most places it goes up across. This is one of my favorite chemistry memes. So we have the periodic table, but still make you memorize things anyway. Most of that is, so you don't spend a ton of time with the periodic table trying to figure out where an element is. Plus, there's all these elements like antimony and tin, where if the periodic table doesn't have the names on it, you'd have a hard time finding antimony or tin from the names, or like silver and gold. So there's stuff you gotta know. Mendeleev's predictions did a pretty good job, actually, of predicting properties of elements that weren't discovered yet. So he said the atomic mass of, called it, I think it's Eka aluminum. So gallium, he said if there's an element under aluminum, it would be, called it Eka aluminum, and that it would be, have a mass of 68, and that's pretty close to the 69.72, which should kind of be more interesting to see what the most abundant isotope is instead of using the average isotopes, but this is the average isotope. He predicted that it would have a low melting point, and it does. Gallium will melt in your hand. And even got like the density formula of the oxide and formula of the chloride pretty close exactly for those. So really did a good job of predicting properties just by using the periodic table without anything else. Because this is back in, this dude, wait a second. There's got to be a typo there. It's a Benjamin Button situation, so everybody, yeah. And anyways, 1800s though. So none of this stuff that we had just talked about, like Einstein figuring out that waves have particle-like properties and particles can have wave-like properties, that's like 1905. So 100 years prior-ish, 70 years prior, this dude was coming up with these things and sorting out this periodic table and making these predictions just because other elements around it he thought would be similar. But the Mendeleev's periodic table, like, he can predict stuff because there are trends, but says nothing about why those trends exist. So it's, I guess in that way, it's empirical. So did experiments or used existing experimental data to predict properties of new elements. Quantum mechanics, though, as we just talked about, explains a lot of the why for different things, especially where it considers electrons. So now we get to do electron configurations. So quantum mechanical theory describes the behavior of electrons and atoms, and we know that they exist within orbitals and that each electron inside of, or I guess around a nucleus, is going to have its own, basically, quantum descriptors. It's going to have the energy level, it's going to have the angular momentum, it's going to have a L, M sub L, and M sub S unique descriptors for where it is. And then a simpler description, though, is to just use these electron configurations. So for hydrogen, we can say 1 is the N, the L is S, and there's 1 electron that's in that orbital. Most of this should be review. So for Schrödinger's equations, we can show that hydrogen's 1 electron occupies the lowest energy orbital in the atom, but it can't be exactly solved for multi-electron atoms. Because as soon as you have more than 1 atom, now you don't just have the nucleus interacting with a single electron. Sorry, I think I said the wrong thing there. But as soon as you have more than 1 electron, the electrons interact with each other. And those interactions complicate things. So the more electrons that you have, the more complicated those interactions become because all of the electrons are interacting with each other and with the nucleus. Yeah, so approximate solutions, though, so not exact solutions, show a lot of the orbitals to be hydrogen-like. So 2 additional concepts affect the multi-electron atoms, and that's where we add that spin, that's the M sub S, and energy splitting of sub-levels. So sub-levels within a level, your main energy level was N, right, so we could have N equals 2. The sub-levels there would be S and P, and those sub-levels end up with different energies because of these electron interactions. We can also use orbital diagrams. So instead of just writing that there's 1 electron, instead of writing this as H1S1, instead of just saying there's 1 electron in the S orbital, we indicate also what that 1 electron spin is. Or if there's more electrons, we indicate what all of their spins are. And to a certain extent, indicate which orbital they're in, or which orbital of the sublevel. And we've talked about spin. You can have plus 1/2 or minus 1/2. So just by convention, an arrow pointing up represents plus 1/2. Right? Pointing up, positive spin. So if you had any random group of hydrogen atoms, half of your electrons would have spin up, half would have spin down. Then the Pauli exclusion principle is really just this idea that no 2 electrons in an atom may have the same 4 quantum numbers. So I guess we had hydrogen or hydride, we had H minus, right? That would be 1s2. But for each of those electrons, we'd need at least 1 quantum number that was different between those 4 quantum numbers. Right, so for one of those electrons, n would equal 0. Wait, n would equal 1. L would equal 0. M sub L would also equal 0. M sub S would be plus 1/2. And for the other electron, most of those quantum numbers would be the same, right? Because they're in the same orbital, they're in the same level, they're in the same sublevel, they're in the same orbital even. But M sub S would be minus 1/2 for one of those electrons. So they always have to have opposing spins, and that's why in an orbital diagram, which I don't mind if you do your orbital diagrams as boxes or if you just use a line. So if you did 1s or 1s, then this would be 2 electrons. That would also be 2 electrons with opposite spins. Either way is Gucci. So if we know the number of orbitals in a sublevel, basically you just multiply that by 2 to know the number of electrons that could be in that sublevel. So the S sublevel has 1 orbital, so it has 2 electrons. P is 3, so it has 6 electrons. D is 5, so it has 10. F has 7, so it has 14. That should really be a review from Chem 20. So every orbital holds 2 electrons, opposite spins. And here's just those quantum numbers again. So 1, 0, 0, 1/2. They have to exist in different states inside of the orbital. Okay, so sublevels in each principal energy level of hydrogen all have the same energy. So the orbital energy in a hydrogen atom only depends on n. So if you go from the lowest energy level, it's going to be n equals 1. If you go up to n equals 2, up to n equals 3, up to n equals 4. Each of those orbitals, there's really only one orbital at each level. And because those are the same, right, for each level, we describe them as degenerate. So they don't really follow what all of the other atoms do. Kind of wanted to find like why use the word degenerate. It makes me think of, have you seen the TV show Letterkenny? Oh, it's hilarious. Canadian TV show. It's very funny. Have you seen it? No, okay. You should check it out. Unless you're offended by strong language, then don't check it out. It's on Hulu. So for multi-electron atoms, the energies of the sublevels are split, not degenerate. So degenerate means that all of those orbitals would have the same energy level. They're not degenerate, they're split, so they have separate energy levels. So they're not, in the sense, broken down so that they're all the same thing. There's differentiation between them. The differences in energy levels are caused by charge interaction shielding and penetration of the electrons. So it's really all of these electron-electron interactions that cause these energy levels to have, or have these orbitals or sublevels to have different energy levels. And this is, you've probably seen, I'm going to draw this diagram in here. Probably seen like this diagram where you've got, I'm just going to use an E. All right, so energy. So as we go up, it's going up, and then we've got the 1s, the 2s, and then there's the 2p, and then you'd have 3s, and then 3p, that kind of thing. That's what I mean by the sublevels have different energies. In the hydrogen atom, if I'm not misinterpreting this, 2s and 2p would both have the same energy. So it doesn't matter if that electron gets excited up into a 2s or a 2p. The only thing that matters is that this is n equals 2, because there are no other electrons for it to interact with. So that single electron goes up into that orbital, and it doesn't really matter where it goes because it's not interacting with any other electrons.
Just for hydrogen.
That's just for hydrogen. Yeah. And then if you went up, they would still all be the same, and the only thing that matters is n equals 1, n equals 2, n equals 3. For anything else, there's different possibilities. So let me write that. This is only hydrogen. Everything else has these split energy levels. This just kind of gets thrown in here. So it's Coulomb's law, which is the potential energy for two charged particles. So if you had any two charged particles near each other, the energy, the repulsive or attractive energy between them is going to depend on how much charge each of those has and the distance between them. This epsilon, probably epsilon naught or epsilon 0, is a, what is it, magnetic permittivity constant. It's just a constant. So if you get farther away, we divide by a larger number and the energy is less. If either of the particles has a higher charge, then we have more energy. So we looked at this, we were talking about we did the orbitals lab, and we had these diagrams. Like one looked like this, and then there was another one that was probably something like this. We said that the difference in these, the difference in say this and this, that energy difference was smaller than for two other orbitals. I think it was like 1s to 2s versus 2s and 2p. Something like that. And then this on the bottom here was a radius from the nucleus. So the closer you are to the nucleus has a positive charge, ones have negative charges. The closer you are to that nucleus, the smaller r is, the more energy there is in that attraction between the two particles, if we're talking about electrons like particles. As you get farther and farther away, less and less energy. This is important because this is why there are different energy levels. For each electron in a multi-electron atom, it experiences both the attraction of the nucleus and repulsion by other electrons in the atom. So the repulsions, so electron repulsions, cause the electron to have a net reduced attraction to the nucleus. So if I draw this as a super simplified thing, we've got the nucleus. And let's just, for the sake of this, treat the electron like a particle. So if I have this, which is, I don't know, let's just say this is neon. So there's 10 protons in here, so this is a positive 10 charge. And we've got an electron here, and that's a negative 1 charge. There's another electron that's on the other side of that electron. This one also has a negative 1 charge. And while this electron is experiencing the full effect of being right up next to the nucleus, this electron on the outside is being blocked by the electron that's in the way. So it's experiencing some repulsion because it doesn't want to get closer to the electron, but it's still attracted to the nucleus. So there's kind of two forces working against each other there. Repelled from one, attracted by the other. And this actually is the effective nuclear charge, which is going to tell us an awful lot about these periodic trends on the periodic table. Okay. So essentially, the closer that an electron can get to the nucleus, the better it is stabilized by that energy of the nucleus, and the more it can work around or work through the repulsion of the other electrons. So the electrons want to get close to the nucleus. And that brings us to this idea of penetration. So the electrons are blocked, outer electrons are blocked by inner electrons, but some of the orbitals, actually, I should say, each orbital has a different ability to penetrate through the electron cloud or through the electron repulsions of the inner electrons to get closer to the nucleus. And we hadn't talked about it yet, but this is what you saw in that molecular or in the atomic orbital lab. Yeah, so degree of penetration is related to the orbital's radial distribution function, and that was these graphs that we had where it was something like this. And we had a bunch of different ones. You looked at them, and this is the radius. And it was actually some factor multiplied by the Bohr radius. Yeah. So just a sort of cartoon look at this, similar to the one that I drew. So out here, this electron, if it's outside of these two other electrons, and remember, they're like waves, they're also like particles, it is only experiencing 3 minus 2 of the charge of the nucleus, because it's being blocked by those two other electrons. If this electron can get in closer to the nucleus, then it can experience the full charge of the nucleus. And that's determined by these functions. These electron spatial distributions. So I pulled these ones up. Yeah. These are the ones from the book. So the 2s orbital has this little distribution inside of the 2p. So the 2s here is actually penetrating inside of and getting closer than the 2p is. And so that actually lets it have lower energy than 2p. So again, if I draw this, it's not like this, more like this. E, energy is increasing. So our 1s, and then our 2s, and then the 2p is slightly higher energy. Because the 2p is basically spending all of its time under this curve, where some of it is inside of 2s, but because 2s has this little lump inside of here that's inside of the 2s or the 2p, that means it's better at penetrating through the other electron clouds and getting closer to the nucleus, and therefore having lower energy. Lower energy because it's stabilized by the nucleus.
So the more area that I guess that curve has the purple area, or
this purple one is the 1s. Just how close it is to 0, essentially.
oh,
Yeah. This picture is okay. I have a better picture. But yeah, this is why the 2s is lower in energy than the 2p. I think, actually, explain real quick that you're talking about that this is lower energy because it's closer to the nucleus, which means it's more strongly attracted to the nucleus. That's more stable. It also means if you wanted to start ripping electrons off, we'll talk about ionization energy later, but if you want to start ripping electrons off, it's harder to remove those electrons because they're already so close to the nucleus, because they're already so stable. Yeah. So That's the penetration through the other sublevels that allows each of these principal sublevels to not be degenerates, to be degenerate. So in your fourth and fifth principal levels, if you remember back to Chem 20, filling in electron configurations, by the time you get to 3, right, you do all the 3s, you gotta go through 3p. You don't fill in any of the 3ds yet, but you go to 4s and then you fill in 3d. The penetration of the 4s and 4p lets those be lower in energy than the 3d. Because it's the 4s being lower than the 3d, because this gets filled afterwards. Yeah, and then as you get farther and farther away, separations between energy levels get smaller and smaller, the same way that when we looked at the principal energy levels of a hydrogen atom, as the electron is jumping farther and farther away, each of those jumps gets smaller and smaller. All right, as you go from n equals 1 to n equals 2 is a huge jump, 2 to 3 is smaller, 3 to 4 is small, and then 4 to 5 is about the same as 3 to 4. So this is that, what I think is a better image. So I've got 4s, 4p, and 3d. And these lines, the color of the line corresponds to the text over here. Oh, can't really see that. That is hard to see on the projector. Make this, that's about the same. Is that going to be way too thick? No, that's fine. Oh. So these are corresponding to the peaks of the, that last one is black and this one's blue. So these large red ones are the peaks of 4p that go inside of the 3D. So that's how 4p is able to penetrate closer to the nucleus and really get around some of that shielding better than 3D, where 3D is mostly completely on the outside of 4p and 4s. And then 4s gets even closer, so the first 4s is here, the second 4s is here, and the third 4s even lines up with the second one from 4p. Yeah. Yes. Yeah, there's more attraction, so it's held on more tightly. Yeah. Closer to the nucleus equals more stable. All right, so this is the idea of penetration. These are actually, I pulled these from that atomic orbital lab and just pulled up the simulations for each of these. All right, so here's the general ordering for orbitals. I've drawn this out roughly a few times. You can see 1s is lower in energy than 2s, and then it's 2p, and then it's 3s, then it's 3p, then 4s, and then you finally fill in the 3d. And then the difference between 3d and 4p is tiny, right? It's really just a small jump. And so this is also the order that you fill in electrons. So orbital filling, the Aufbau principle, really, there's all these fancy names, but it really means that you fill in electrons from the lowest energy first, right? So 1s is the lowest energy orbital, so you put the electrons there first. You fill it from the bottom to the top. So lower energy orbitals filled before higher energy. Orbitals in the same sublevel have the same energy, roughly. And then your filling order is going to be 1s, 2s, 2p, 3s, 3p, 4s, and then the 3d gets thrown in there. Now, depending on probably who you had for Chem 20 or how you were taught this in high school, they might have written the 3d before 4s, just so that they all go in order. I don't think most people do that, but I think some people do. I always write the 4s because I write them in the order that they get filled. And then we also apply the Pauli exclusion principle, where those spins have to be opposite. And then Hund's rule, when filling degenerate orbitals, electrons fill them singly first with parallel spins. By degenerate orbitals, it means like 3p. Oops, I forgot that that's thick. So 3p, each of those suborbitals, we treat them as having the same energy. So you'd fill them one first, and then add the second one in. So all the same electron configuration rules. The quantum hotel is an analogy for this. if you took my Chem 20, it probably said Mrs. K's Chemistry Land, and that's because it was my mom's, but I've inherited the hotel. She didn't die, she just retired. So you can think of this as like a hotel, and it's a discount hotel. There's no getting a room ahead of time. When you show up, you get a room, and they just assign rooms from the bottom of the hotel to the top. So when you show up, at the lowest energy, the cheapest rooms are on the first floor, and actually there's only one room on the first floor. So you get just the 1S room. On the second floor, now you've got the 2S and 2P. On the third floor, it has 3S, 3P, but we don't like to fill 3D until we filled 4S and 4P, because D has 5 beds in it, right? So then each of these rooms has a different number of beds that corresponds to the number of orbitals. S has 1 bed, P has 3 beds, D has 5 beds, F has 7 beds. And in general, people don't want to share beds because we also don't assign people to their own rooms. If you're guest number 1 and a stranger guest number 2 shows up, you guys get the same room. Because that's the cheapest way to do things. Yeah, so money equals energy also, right? So the cheapest rooms are on the bottom. And then since you're sleeping with some random person in this bed, you sleep head to feet, opposite spins. So if we were to fill this in for any of these elements, we could choose, I don't know, oxygen. Actually, I always do oxygen. Let's do fluorine. So we fill this in for fluorine. Fluorine has the same number. If it's neutral ground state fluorine, it's going to have the same number of electrons as it does protons. So how many electrons does fluorine have? 9. So then we start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9. And when you're filling these in, I would just, even though if you know that this is going to be completely filled in the 2P, just fill them in one at a time first, and then fill them in with the second one. So you get used to that idea that if you run out of electrons and you stop, then you've already done the, is it Hund's rule? No, it's Hund's rule. Yeah, singly first with parallel spins. Now you could technically fill them with all downspin first if you wanted to, as long as they all have the same spin. Unless stated otherwise, electron configuration will refer to the ground state. So this would be the ground state for fluorine. There could be some excited state where one or more of these electrons ends up in a higher orbital. Don't think we do that in this class. We might. Actually, I think we do talk about HOMO and LUMO, maybe. Highest occupied molecular orbital. That'll get into when we've got 2 things with bonds to each other where the electrons fill those. But for now, just ground states. Yeah, number of electrons in a neutral atom equals its atomic number. That's pretty easy, as long as you have a periodic table. And then electrons with parallel spins have correlated motion that minimizes their mutual repulsion, which it just seems funny that the mutual repulsion, like they all hate each other. That's just the idea. They try to stay away from each other because they have the same charge. But yeah, there's a special stability when all of the electrons are spinning in the same direction, and when each of them is 1 to an orbital. And again, we covered this earlier, but each sublevel has a different number of orbitals, and then you can have 2 electrons per orbital. All right. Oh yes, we can do shortcuts. So instead of writing out all of rubidium's electron configuration starting from hydrogen, we can instead say that the inner electrons can be represented by the same electron configuration as krypton. Yeah, so krypton, and then rubidium's here. So then all you have to do is krypton in brackets, and then 5s1. If I ask you to write the electron configuration for krypton, please do not do krypton. Yes. Actually, I think I have a meme. I'll find that later. There's like a Buzz Lightyear where his head's all stretched out, and he says, yes, the floor here is made of floor. Yeah, so that's the same vibe.
Can we do rubidium minus?
No. That's... Like, it makes sense, but that's like the way that Yoda talks. It's not grammatically correct, but you know what he's saying.
Yeah.
Yeah. Or from The Office, why use many word when few word do trick? We all know what you mean, but it only works for the simplest statements. So yeah, so some examples here, orbitals, or electron configurations and then orbital diagrams. I do want you to be able to also do orbital diagrams with representing just roughly the energy levels. Like you don't need to get these exact spacings, but to know that 1s is higher, or that 2s is higher than 1s and 2p is higher than 2s, and just be able to do that, because I think it also helps with just doing electron configurations in general. Huh? Yeah, no. Pass out rulers. Okay, so orbital diagram for argon and determine the number of unpaired electrons. So we're gonna do this orbital diagram with the energy levels. So we'll do the whole thing. How many electrons does argon have? Yeah, 18. So it'll be the same as the number of protons. And so first it'll be 1s, then 2s, and then 2p. Actually, yeah. 3s, 3p. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. So how many unpaired electrons are there? Nada. None. Zilch. So yeah, 0 unpaired electrons. If we had done phosphorus instead, let's say this one's for argon. So how many unpaired electrons? I'll just leave the argon one here for now, but how many unpaired electrons would phosphorus have? So argon has 18 electrons. Phosphorus has 15 electrons. Yeah, so I'd remove 1, 2, 3. We'd end up with 3 unpaired electrons. So yeah, practice using the periodic table to do these, because it just kind of makes things easier. There's a correspondence. Oh yeah, valence electrons. Been talking about these a lot in Chem 20. For your main group elements, number of valence electrons is really easy. It's the same as the main group number. So lithium is in main group 1, so it's got 1 valence electron. Beryllium is in main group 2, so it has 2 valence electrons. Boron would be 3, 4, 5, 6, 7, 8, and then that applies all the way down. Yeah.
We were just talking about how phosphorus has a -3 charge.
Yeah.
Is that a trend?
Yes. Absolutely. Yeah, that is a trend. So yeah, phosphorus has 3 unpaired electrons. And did we talk in this chapter about the octet rule? Maybe?
Yeah.
It's not in this chapter?
Yeah.
Might be the next chapter. When we do Lewis structures and stuff, we'll talk about the octet rule. So if you have 8 valence electrons, that has a special stability, because the entire shell is completely full. And so the main group elements at least are either gaining or losing electrons to get that octet. So, right, if we count these electrons, there's 1, 2, 3, 4, 5, and we would add 3 more, would give us 8. And if we gain 3 more electrons, then we'd have, let's see what phosphorus is. So it'd be 15 protons. So it'd be a positive 15, and then it would have 18 electrons, which is a negative 18. So 15 minus 18 is negative 3. The same trend applies on the other side of the periodic table too. So for lithium, would lose 1 electron, which would give it a 1+ charge. Yeah. Astute observation. Yeah, so the main group elements, easy to pick out what their valence electrons are because it's their main group number. And by main group number, I also mean not the 15. These don't have 15 valence electrons. It's this, in Roman numerals, 5a. So nitrogen has 5 valence electrons. Phosphorus has 5 valence electrons. Arsenic, antimony, and bismuth would all have 5 valence electrons. Doesn't work for the transition elements. but it does work for those. And then anything that's not a valence electron is a core electron. So anything on the inside is a core electron. So actually, let's do phosphorus again. Actually, we do arsenic. Let's move down a row. So just the electron configuration for arsenic. And this will be, I'm going to do the whole thing. 1s2, 2s2, 2p6, 3s2, 3p6, 4s, that's not an s, 4s2, 3d10, 4p3. So how do you find the valence electrons? The valence electrons here are going to be anything that's in the n equals 4 energy level. So for your configurations, it'll always be the electrons associated with the highest n number. So here, that's 2 s electrons and then 3 p electrons, so it's got 5 valence electrons. And then how many core electrons does arsenic have? Yeah, you could just subtract the 5. No, that's a fine way to do it. The other way would be that you could count up anything here that's not in the n equals 4, including the 3d10. But yeah, subtracting 5 would also work. So since its atomic number is 33, subtract 5 from that. What would you say is 28? Yeah. So 28 core electrons. That also corresponds to the electron configuration of argon is 18 of those. But then since we added these 3d10s, those are also core electrons. So once you get up past argon, then it's going to be the same as the previous noble gas plus 10. So those are all in lower energy levels. Yeah, the valence electrons, though, are what really tell us a lot. Any other questions? Yeah. Xenon would be kryptons plus 10. So you notice here it goes 2, 10, and 8. These are all intervals of 8. And then when we make this jump, it's 18. And then this jump is another 18. And then this jump's another, actually, this jump includes these, the F block. Just know that you have to count all of the electrons before, which if you're in the P block, so this is the S block because their last valence electron is in the S orbital, or is in an S orbital. This is the P block because their last electron's in a P orbital. This is the D block because their last electron's in a D orbital. Even though here they're not valence electrons. But if you're in the P block, then you have to include all of those D electrons. So valence electrons, and it's those valence electrons, again, like you were saying, with the phosphorus wants to gain 3 more valence electrons to get to the same electron configuration as argon, which is why it forms a 3- charge. This is just a table from the book that only has the valence electrons. And then it's only everything up to argon. Oh, and then one of the periodic trends that these valence electrons explain is why like the noble gases are all neutral, because they all have the same number of valence electrons. So for any column, their properties, similar properties, are largely explained by having the same number of valence electrons. Oh, we did phosphorus already. Somebody pick another element. Don't do hydrogen or helium. Copper, fun. So copper, you do copper. We're going to talk about exceptions in the D block. Huh? There's some interesting exceptions that happen in the D block. It actually ends up being 3d10, and there's nothing in 4s. That's why you picked it, huh? Yeah, okay. All right, aluminum. So this will be 1s. Oh, here, guide me. What's next? 1s2? 3p1. All right, what should I circle for the valence electrons? Yep, there's the valence electrons. Maybe I should like highlight, there you go, highlight valence electrons. And now what are the core electrons? Yep. So we've got 3 valence electrons and 8 core electrons. Great. Oh, I guess I mentioned this already. We can divide out the periodic table into 4 blocks depending on where their last electron ends up. Like the group number of any main group element is equal to the number of valence electrons, and the row number of a main group element is equal to the highest principal quantum number of that element. So, like I was saying, the highest for any row, so if you're in a main group element, so that's the S block, which is again group 1 and group 2, and then the P block, which is 3A through 8A, that's going to be your highest. Aside from the few exceptions, the highest energy orbital or the highest energy level does also apply to most of the D block. But we've got S, P, D, and then this is F. And then if you didn't know this, the periodic table should actually have this inserted here, and it should be like more than twice as long. But that's super impractical, so nobody does that. Turns out the, universe wasn't considering what the aspect ratio of our pieces of paper would be when they created the periodic table or created the elements. Thanks, universe. Yeah, okay. And here they are nicely highlighted in color. So notice too that helium up here gets pushed over to the noble gases because it behaves like a noble gas. And that's because helium follows the duet rule, so it only needs 2 electrons to be happy and stable. But it is part of the S block because its last electron is in an S orbital. Yeah, so we can use the periodic table to write electron configurations much more quickly. I don't know if it's much more quickly. It's probably about the same. If you look at the periodic table, so for this example, chlorine, we can use this noble gas neon as a shortcut. And then you essentially look at where is it past each of these orbital blocks. So if it's past the S block, then 3S is going to be filled because it's in the 3rd row. And then you fill up to whatever its place is in the P block. So it's the 1, 2, 3, 4, 5. It's the 5th place in the P block, so there's going to be 5 electrons in the P orbital. And the same mostly applies for D. Again, we'll talk about exceptions in D. All right, so using the periodic table, let's do bismuth. So bismuth is, we've got a big periodic table up here. Bismuth is down here. Point at it right here. So which shortcut would we use? Xenon, not Xena, warrior princess. And then what? Yep, 6s2. Yeah, it goes down 2 for F. So 4F14. 5D10. Yeah. It's a lot, I know. Lanthanides. Lanthanides and actinides. Yeah, lanthanides and actinides is the F block down here. Yep. There it is. I won't make you do the energy style orbital diagram for something like this. You could probably like suss it out from the fact that this is going to be lower than the 4 based on where it fits, right? Like it's going to be higher energy than the 4s, but that's a lot. Electron configurations. All right, I'm going to practice more of these. It's good practice. So for chlorine, which shortcut would I use? Neon. So you always go to the previous row, and then 5. And for silicon, neon, 3s2, 3p2. Very similar. Strontium, though. Yeah, so strontium's over there. Krypton is the row above that, 5s2. And oxygen. So you can practice these. Just write a whole bunch of them down. Just pick any element. There's probably 86 that I would actually give you. 86 possibilities. I'm not going to give you all 86. That'd be a brutal assignment. All right, do them all without shortcuts. Yeah, so there are some of these irregular electron configurations. Like, for example, the 3D, the 4s is lower energy than 3D, therefore the 4s fills before the 3D. So, yeah, n-1. But some of the transition metals have irregular electron configurations in which the ns, so meaning like whatever n level it is, s, 3s, 2s, 4s, that kind of thing, only partially fills before the previous d orbital fills. Or it won't fill at all. So those ones have been found experimentally because they're not predicted by this. Copper was one of those. So let's do the orbital diagram for copper. So this is copper. I'm going to take the shortcut here at argon. And so we have this 4s, and then we have 1, 2, 3, 4, 5. Oh, not 5d, 3d. So how many electrons are we going to have to fill into this part of the electron or the orbital diagram? Because it's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if we fill this in, it'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now you could fill this in from the 4s, because the 4s here, I did draw it like that for a reason. The 4s is lower in energy. Actually, maybe I'll back up to that step here first. So there's a special, basically, I think nature in general likes to be balanced, just like Thanos wanted it, just like all things should be. So if you can have balance, if you can have symmetry, if you can have everything lined up together, that has a special stability to it. So here, even though the 4s is lower energy, if we take one of these electrons away and we add it into the 3D, now all of the 3D orbitals are filled. And that has a special lower energy. So when copper fills in, it will leave this 4s missing an electron. And that's pretty much why all of the exceptions happen. I'm going to take a look at, where's this periodic table? Here we go. So another one, some of the other weird ones, chromium. All right, so these ones fill as expected, 4s1, 4s2, and we've got 4s2, 3d1, 4s2, 3d2, 3d3, 4s, oh, look at that. 4s1, 3d5. So if we take a look at that, so 4s would have 1, 3d has 1, 2, 3, 4, 5. Yeah. Anomalies, exceptions. A little bit. I guess if you like really wanted to be on the safe side, you can draw the orbital diagrams out for these things, at least for the sort of last row of electrons that you have to fill in. And if you see that, because if you did this normally, you would write this, and you could see that, oh, there's 4 electrons in the D, and as a principle, general overarching principle, the atoms, the electrons, are more happy when each of those is either singly filled or when they're doubly filled. Because this trend also follows not just for chromium, but if we move down, does it for molybdenum too? And I bet, no, that's 6s. So it breaks down as you go farther because the energy levels, I think, get closer and it matters less. But so those do that. Actually, wow, blanking, niobium or neodymium? Neodymium might be just the magnets, but NB here does 5s1, 4d4. So it moves an electron over. I think the ones that I really care about you knowing are like the chromium and then the copper. So chromium, molybdenum, copper, and silver. If you start getting lower on the periodic table than that, then again, the energy levels get closer and closer together. Other weird stuff can happen. Yeah, Cody.
Will these ever happen?
I think so. Well, here's a weird one. 6s2, 4f7, 5d1. I don't have an explanation for that one. Like I said, other stuff happens as you start getting farther down, and there's probably more splitting that happens too. Yeah, 6s2, 14f10, 5d1. Again, maybe we can narrow it down to these four. Palladium's an interesting one too. It's just 4d10. Completely leaves out the 4s. So there are those anomalies. Oh, good. Here's more of them. Yeah, so palladium, because these are the expected, these are the experimentally. And again, it's either half filling or fully filling that D block. 4d7? I think that if you take Chem 2, there's talk about coordination compounds, and I don't know if ruthenium does something like that. You can essentially stabilize these other electron configurations and further split the d orbitals. Anyways. Chemical properties of elements are periodic because of the number of valence electrons. That's why each group has the same number of valence electrons, so they have similar properties. So elements in a row show a pattern that repeats. So as you change the number of valence electrons, the properties change in a predictable way. And that kind of makes sense why it's stacked up like this then, because if you have one valence electron versus two valence electrons, that's going to be the same as it is lithium and beryllium, sodium and magnesium repeat that pattern, and then so on and so forth down the periodic table. So those sort of two properties lock the periodic table into this configuration. Yeah. So to explain, the quantum mechanical model explains this because the number of valence electrons and the types of orbitals they occupy are also periodic, so that I think it's easy to think of this first and then try and apply this to quantum mechanics, but it's really quantum mechanics that makes this happen. So like when you looked at all of those orbitals on the atomic orbital lab, the simulation, right? Each of those has a very similar shape. They change a little bit and they have different nodes and things as they get to higher and higher energy levels, but they all have the same repeating shapes. And so those electrons fill in a repeating pattern, and those properties of the atoms come out of those repeating patterns in the orbitals. All right, we'll just real quickly run through these patterns. So the noble gases all have 8 valence electrons, and they're all pretty inert. Actually, really inert. I guess helium and neon are practically inert. You can make some of these higher level or higher energy or larger, I should say, noble gases can do some chemistry. You can force them to make some reactions. For neon and helium, they're so small that nothing happens. Yeah, so electron configuration is stable, again, because of those 8 valence electrons. Now, if we move to the other side of the periodic table, which is really just one electron different from the noble gases, we get the alkali metals, which are all super reactive metals. They're really reactive because they really want to give up that one electron to have the same stable configuration as the noble gases. So they undergo any reaction possible to lose that electron. And because they're losing one electron, they all form +1 ions, or 1+ ions. Flip-flopping, again, one electron away from noble gases, they have the halogens, which instead of wanting to lose one electron, just want to gain one electron more than anything in the world. More than anything in the world, Ron. Sorry, Anchorman reference. So they just really want to gain one more electron so they can, again, have this noble gas configuration. That makes them highly reactive. Chlorine is nasty stuff. Fluorine is terrifying. Very reactive, and then since they're all trying to gain one electron, they all form 1- charges. And these are patterns that repeat a lot on the periodic table. So group 1 is all +1, or 1+. Group 2 is all 2+. 7A is 1-. 6A is 2-. 3A, there's not as many of them, but nitrogen and phosphorus and arsenic do follow that same pattern of 3-. Breaks down a little bit after that. Yeah, so they all form ions that result in those electron configurations that are stable. You can see a bunch of those here. Aluminum does this also. And actually, if we look at Oh, I guess in my Chem 20, I have them memorize aluminum, gallium, and indium. They all predominantly form 3+ charges because they have 1, 2, 3 valence electrons to lose before they get to a noble gas. And scandium actually will also do that. So it'll lose that d orbital one of those d orbital electrons so that it doesn't have any, forms predominantly a 3+. Zinc and cadmium, they form 2+ charges, losing those 2 4s electrons because they each have a full d block. Silver pretty much exclusively forms a 1+. So it's got the 2, 4, or I guess what is this? 1, 2, 3, 4, 5. So it's got 2 5s electrons. It also has one of those irregular electron configurations where it'll be 4s1, sorry, not 4, 5s1, 4d10. And so it just loses that 1 4s or 5s electron to make that 1+ charge. So even for some of these transition metals, the fact that they're losing electrons to get to stable electron configurations explains their charges. Can write this on here. Silver. Oh yeah, so for anions, they're essentially making their electron configuration the same as the closest noble gas. So sulfur gains 2 electrons to become like argon. And then they'll have the same electron configuration. For the cations, they're again losing electrons to get essentially back a row, so they wrap around. So calcium will lose 1, 2 electrons, and then it'll have the same electron configuration as argon. Or magnesium having the same configuration as neon. Okay, I guess we'll stop there at atomic size. It's really just a lot more trends. And don't forget this idea of effective nuclear charge. This is the whole equation for effective nuclear charge to calculate it super simply as far as we need in this class. And what it comes down to is the number of protons in the nucleus is Z minus S, which is the number of core electrons, ignoring valence electrons. So for sulfur, we want to calculate the effective nuclear charge on its valence electrons. So this is essentially how much the valence electrons feel the pull of the nucleus. And so it would be 16 minus 10. So the effective nuclear charge of sulfur would be +6. And then +7, +5, +4, +3, +2, +1. And then if you go down, sulfur, selenium is also going to be, wait, selenium might be one of the ones, weird ones where it flops. Because it'd be 34, it's going to be 34 minus 10 d electrons minus 18. So it would be still 6. Still 6, right? Yeah. 34.
Oh,
Minus 18. Yeah, so it's still 6. So all of these also have an effective nuclear charge of 6, not accounting for the fact that the level of shielding changes with the orbital and that kind of thing. But we're not going to go into that. But again, a lot of these periodic trends in terms of like size and stuff depend on that nuclear charge.